All right. So, okay. Well, thanks for coming to class today. And so today will be a little bit of a review. I'll go over the what we're going to have on the final, and then I can go over the answers to the practice problems that I've posted online. And yeah, and that's the plan for today. So the final exam will be on Friday, and you can either take it at 10 a.m. or 8 p.m. Pacific time. You'll log into Zoom right here on this link. Okay, so just make sure you you log in. Most of you got it just fine. Did that just fine during the midterm. Same idea. And you will have your camera on, your mic's muted, and that will be it. The exam will be 2 hours long, I should say. 2 hours long. Or I don't know, maybe, yeah, 2 hours. Maybe we'll say 1:55, 1 hour 55 minutes. I think that should be fine. 1 hour 55 minutes long. Okay. And this is kind of the breakdown for the questions, which will be we'll have some kind of conceptual definition / conceptual problems that cover chapters 7 to 9, and I actually posted a few practice problems under the conceptual practice on CCLE. Okay, and then and this should be about 2 to 3 questions from the assigned journal article. So last week I gave you a reading assignment instead of a lab, and I don't know. I hope that assignment was at least enjoyable, and I hope it was neat to see kind of the stuff that you've been learning in class being used in a kind of a real life research setting. And so anyway, I've got some questions related to the reading there. Then you also have a few questions covering the conditions to use the central limit theorem. So I decided to separate out the questions for checking the conditions into kind of their own questions, because what I didn't want to do was to write out a problem and then the answer is, ask something like, hey, what's the p-value in this situation? And then the answer is actually, you can't calculate a p-value because the conditions aren't met. So the way it's going to be done is that there's just going to be separate questions where I'll just kind of describe a scenario, and then you will tell me if the conditions are met or not met. And you have a couple examples of that in the practice problems for the final. And then there will be maybe a handful of questions that cover chapters 1 through 6. So they're mostly going to be just definition and conceptual questions. So there's no actual, say, calculation-based questions for chapters 1 through 6. Just mostly definition and conceptual there. And then the rest, which will be kind of the bulk of the exam, will be about 20 to 25 calculation-based questions from chapters 7 through 9. Okay, and I think I've provided lots of practice problems for this. For these types of questions. All right, and then and the whole exam is going to be multiple choice. So that's going to be the plan. So that will be Friday, September 11th at either 10 a.m. or 8 p.m. Okay. Are there any questions regarding just either the logistics of the exam or anything else? So I'm going to be putting in problems that require the use of RStudio. No, there will not be problems that require RStudio. You can choose to use RStudio as a calculator, though. So if you want to use the RStudio as a calculator, you are allowed, but you will not be required to use RStudio. So if you want to use, say, the p-norm function on RStudio, or use the pt function for kind of like the t-table and whatnot in RStudio, you're allowed to use that. But you aren't required to. You can use the tables and also just be fine. Okay, so I'll post that document. Okay. Maybe we'll go over these conceptual practice problems first, and then and if there are any requests for either the Chapter 8, Chapter 9, or the practice problems, we can do those. We probably won't have time to go over all the questions, but I've posted up the answers, so I'm hoping that will be enough to kind of get you through it. So let me bring this up. Okay. And we'll start off with this. It says, so the first question here is that the significance level alpha is used to decide whether or not to reject the null hypothesis. And what else is alpha equal to? So this comes just kind of straight from the notes. Alpha is equal to probability of a type 1 error, or the probability type 1 error is the same thing as a false positive. So false positive is when we reject the null hypothesis, but the null hypothesis is true. So mistakenly rejecting the null hypothesis when the null hypothesis is true. So the answer to number 1 is A. Okay, you know what? I actually did not cover this, so you can actually skip this problem. So this was not covered in lecture, so I apologize. I just put up the file for practice problems from previous quarter, and I did not cover what beta was. But just so you know, and but I won't test you on this. Beta is the probability of a type 2 error. But if I ask the question, what is a type 2 error, that would be, this is the false negative. And that means we did not reject the null when we should have. False negative. Mistakenly not rejecting the null hypothesis when the null hypothesis is false, when we should have. Okay. Okay, and a type 1 error, that's the false positive. So that's when we reject the null when the null hypothesis is true. All right, that's straightforward enough. And then again, as I'm going through any of this, if any of this you have questions about, just let me know, and we can spend more time on a certain topic. All right, let's go ahead and take a look at these questions here. All right, number 4 says, imagine a criminal court case with the following hypotheses. The null is that the defendant is innocent, and the alternative is that the defendant is guilty. And we'll say, based on the way the American justice system has been created, would we want a large or a small alpha? So a type 1 error is the false positive. And that would be rejecting the null. So we're convicting when the null is true. So that means we convict an innocent person. Okay, and then the type 2 is the false negative. And that is letting a guilty person go free. Okay, and so so the way our justice system is set up is that we would prefer to make a type 2 error over a type 1 error. Okay, both of these things we want to avoid, but we would, if we have to make a choice, we would say the type 2 error is worse than, I'm sorry, the type 1 error is worse than the type 2, so we would rather make a type 2. So the type 1 error is worse than the type 2 error. So we prefer to make a type 2 error. So alpha is equal to the probability of type 1. So we want to reduce the risk of a type 1 error. So we want to pick a small alpha. So we want a small alpha. Type 1 error is worse, so we want a small alpha. Okay. And in this case, for problem 5, we kind of have the different scenario. The patient undergoes some tests to detect cancer, and the tests have the following hypotheses. The null is that the patient has no cancer, whereas the alternative is that the patient does have cancer. So the type 1, that's the false positive. That means healthy person is believed to have cancer, healthy person. And then type 2 is that a person with cancer, the cancer goes undetected. Okay, and so so type 2, this is the false negative, meaning that we don't believe they have cancer when they actually do. So if we look at the answer choices, is that we believe the patient has no cancer, even though cancer actually exists in the patient's body, is going to be answer choice A. So that's going to be our answer there. All right. For number 6, it says, when using a two-sided alternative, this means that the p-value, okay, and we have a few choices, and our choices is that the p-value will always be double the p-value if we use a greater than sign, will always be double the p-value if we use a less than sign, or it might be greater or smaller than the p-value of a one-sided alternative depending on the direction of the alternative. And so a lot of times the p-value of a two-sided alternative is 2 times the tail area, but that's not always the case. So it is possible to have you can have an alternative hypothesis where you say, let's say p is less than 0.6 or something like that. And maybe this is the diagram. And then so if the data come back looking something like this, right? So maybe the null hypothesis is that p is equal to 0.6. The alternative is that p is less than 0.6. And maybe your data comes back with p hat equal to 0.7, okay? So, you put 0.6 in the middle. That's what you would expect if the null hypothesis were true. And then what we observed is p is equal to 0.7. So if anything, we don't have evidence that p hat is less than 0.6. If anything, we have evidence that it's greater. And so our p-value would be whatever our p-value is, it's going to be greater than 0.5. So if we use a two-sided alternative, then it cannot be the p-value of a two-sided alternative. Would be something like this. P is equal to 0.6. The alternative is that p is not equal to 0.6. And if our p hat comes in at 0.7, all right, we would put 0.6 in the middle. 0.7 goes out here. 0.7 is 0.1 or 10 percentage points away from the middle. And so the two-sided alternative would look like this, which, is not going to be double. So double this is over 1, and this is certainly less than that. Okay, so the answer here for number 6 is that it might be greater or smaller than the p-value of a one-sided alternative, depending on the direction of the alternative. A question came in the chat. It says, would we want a large alpha for number 5? And the answer is yes, okay. In the case of number 5, when the type 2 error is worse than the type 1, we would prefer a large alpha because the consequences of a type 2 error are worse than the consequences of a type 1 error. Okay. Are there any questions on this? Does this feel good? Okay, and then the last 2 questions from the conceptual page. This is what I've got. All right, it says you perform a hypothesis test for proportions with 1 sample. The alternative states that the population proportion is greater than 0.3. Okay, so from this we know a few things. We know the null hypothesis is that p is equal to 0.3, and then the alternative is that p is greater than 0.3. You find that your p-value is greater than alpha, and so we do some kind of test. We don't know the result, but the p-value, whatever it is greater than alpha. So what this means is we will not reject the null hypothesis. So we will say we do not have evidence that the population proportion is greater than 0.3. Okay, do not have enough evidence. We don't reject the null, so we don't have evidence that it is. And we cannot say we have evidence to support the null, okay? And we're not going to say it's not about the sample proportion, and we're not saying, so we can't say that P is greater than 0.3 or something. So this is our answer. Our answer choice is A. If the p-value is less than alpha, then we can pick answer choice B. Okay. For number 8, it says you perform a hypothesis test for population means with the alternative hypothesis that the two populations have different means. With alpha equal to 0.05, the test reveals that you would reject the null hypothesis. If you had done the same test with the same data but used alpha equal to 10% instead of 5%, what conclusion would you have made? So our null hypothesis is that, oh, sorry, not P, but is that the two means, mu1 is equal to mu2, and the alternative is that they are different. And we use alpha equal to 0.05, and our conclusion was that we reject the null hypothesis. Okay, and because we reject the null hypothesis, that means that that means our p-value, whatever it was, is less than 0.05. P-value is less than alpha, okay? Or in our case, our p-value is less than 0.05. Something. Okay, p-value is less than 0.05. And so it says if we did the same test but used alpha equal to 10%, so whatever our p-value is, we know it's less than 0.05, so we also know that our p-value is less than 0.1. Okay, it's some number less than 5%, so whatever that number is, that number has to also be less than 10%, so that means we would also reject the null hypothesis. Now, if the question said, if we redid it with alpha equal to 1%, what conclusion would we make? And the answer there is, answer cannot be determined because, well, we know that the p-value is less than 5%. It can be any number less than 5%. So it could be like 0.001, or it could be, 0.02. And, 0.001 is less than 1%, but 0.02 is not less than 1%. So we don't know what value it is. So we can't tell you whether we would reject or not reject the null hypothesis if we redid it with alpha equal to 1%. But if alpha was 10%, we know that our p-value would be less than 10%, and we would reject the null. Okay. All right, I'm going to go ahead and open up the practice final. Okay, so this is just kind of a practice final formula sheet. Did I provide the formula sheet? Yes, I did. Okay, So this is the formula sheet. And the important thing to note is that this top corner, we did not cover in class. We did not cover proportions to samples, right? So this is the only thing we didn't cover, but we did everything else. And then confidence means one sample will be used for paired, two samples with paired data, okay? So this should say mean, two samples independent. But it, that's just there for your kind of convenience here. All right, so practice problems for the final. This is what we've got. And, I said there's going to be some conceptual questions, and so this is just some summary information there. Okay, so you'll have a section kind of like this, where it just asks which of the conditions were violated. So I guess we'll go ahead and let's take a look. All right, so here it says, these are some of the conditions that might have been violated. And so we've got violates the independent and or randomization assumption, violates the big population condition, violates the large sample condition. I think these are in a little bit different order than how I covered them in lecture, or it doesn't violate any of the assumptions and conditions. All right, so the first question was, a study is performed to understand the relationship between bright lights and headaches, and we gave, we selected 80 randomly selected subjects somehow, and we exposed them to really bright lights, and we asked if any of them experienced headaches, and 20 of them said they have headaches. And then we have 90 subjects, and we gave them less bright lights, and in that case, only 12 of them said they have headaches. All right, and then we want to do a test to see if there's a difference in kind of the proportion that complain about headaches. And so, are any of the conditions violated? To use the central limit theorem, if we want to compare basically two proportions, can we do that? So the independence randomization assumption, that is met. So I'm going to just say this one's met because they are randomly selected, right? So it says randomly selected, so that condition is met. B, the big population, their population is not specifically stated here, but the population would be anyone who might be exposed to lights and might experience headaches, right? So population is anyone exposed to lights, right? So that's pretty much almost everyone. So that's a big population. So big population, that's met. Okay, and then C is large sample condition. So we need, for this, you need n times p and n times 1 minus p, or at least 10 successes and 10 failures. I'm going to go ahead, I apologize for the formatting here. So this one is at least 10 successes and failures in each group. And that's met. Okay, we got 20 and we have 12. Both of those numbers are bigger than 10. And if 20 have headaches, then that means we have 60 that do not. 60 is greater than 10. If 90 and 12, which means we have 78 with no headaches, and that is also greater than 10. So all of these numbers are greater than 10, so this condition is met. So the answer is D. The next one says a researcher wants to make a confidence interval for how common a certain disease in the U.S. is in the U.S. population, and he finds 300 randomly selected subjects. How do we check for independence? Well, so if it says it's randomly selected, I guess, so here, are the two groups independent? And if the subjects are selected randomly, then you kind of have to assume that they're selected independently as well. The independence thing comes into play if, say, you are selecting people randomly, but then you're selecting multiple people at a time. So if it might be kind of like you select a person at random, but then you also select him and his best friend or something like that. And then your sample is no longer random. So if you say, thanks for volunteering, please go get your best friend or your brother or sister or something like that, someone related or connected to that individual, then the individuals are no longer independent. And so, so that's not a good idea. So sometimes you'll see things that'll say like, fill out this survey and then invite your friends to also fill out the survey and things like that. If that's the case, you are not going to get a random or independent sample. And so I always cringe a little bit whenever I see someone go on Facebook or some website and they say, please fill out this survey, and they have like an online form. If you have an online form, if you do a survey via an online form, which is easy, right? You just set up a Google form and then you email that out or you post that on Facebook or something. Please know that you will not be getting a random sample, and your sample is not even going to be close to being representative of anything. And so if somebody posts up a survey and it says, help me, help us out by filling out this survey. I don't even know what the point is of these surveys, because it's not going to be representative of anything. Or if they're just hoping some people say yes and no, then I can tell you that, yeah, some people are going to say yes and some people are going to say no, or whatever the question is. But yeah, internet surveys, if there's, you should know that internet surveys are completely unreliable. And then some groups of people actually enjoy just ruining an internet survey when they find out that some large publication is running a survey. Like, they take delight in just bombarding the survey with nonsense results to just for fun. Okay, here it says a researcher wants to make a confidence interval for how common a certain disease is in the US population. And he finds 300 randomly selected subjects and finds 2% of them have the disease. Are any conditions violated? Okay, so we've got the randomly selected subjects. So condition A is met, okay? And the big population, the population is the US population, which is more than 300 times 10, so that condition is met. And then C, we need at least 10 successes and 10 failures. So 300 times 0.02 is only equal to 6. So this condition is not met. We have less than 10 successes. Or success is a little bit strange to think about a disease. So we have less than 10 yeses. Okay, we've got more than 10 no's, but less than 10 yeses. So this is not going to be a big enough sample. All right, next it says a UCLA student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets, and he finds data from 100 people and finds that 45 of them answered yes to his questions. Are any conditions violated? And this one is going to be A, is not met. It is not random. Okay, going around school, going around the school campus, interviewing people you meet, that will result in a non-random survey, okay? So a lot depends on, where in around the school you are walking. So if you're walking around North Campus, you're gonna encounter more North Campus majors. If you walk around South Campus, you're gonna encounter more South Campus majors. Even if you go to some place like, Bruin Plaza, Bruin Walk, where, you get a mix of students, you're only going to get students who are outside that day. And depending on the day of the week, whether it's a Tuesday or a Monday or something, right? Generally, students either take classes Monday, Wednesday, Friday, or Tuesday, Thursday, and those classes might be different. And yeah, and some students don't attend class, don't stay in their dorm or apartment, don't go out very often. I don't know. So you're not going to get a truly random sample. So that's going to be an issue. Okay. Obviously, this is a pre-COVID situation here, so it's not random. We could check the other things, right? UCLA has a population that's bigger than 100 times 10. And the sample is big enough because we have 45 who answered yes, which means we have 55 who answered no, and both of those numbers are bigger than 10. So the other conditions are met, but the independent random condition is not met. Okay, and then the last one, we've got a company that wants to survey its employees. It has a total of 800 employees, and it decides to select 100 of the employees at random, interviews them if they've had any negative interactions with their coworkers. 25 of them said yes, they've had negative interactions. So it is random, but the big population condition is not met. Okay, the population is 800, the sample is 100. So the population is not 10 times bigger than the sample. So the population needs to be at least 10 times bigger than the sample, and the population is only 800. So that could run into some problems there. Okay, is that good? Do we have any questions there? Okay, so I've got, we have a lot of these problems. I don't know if I want to go through all of them, but do you guys have a, so number 4, the answer to number 4 is violates the big population condition, number 4, because our sample is 100 and our population is 800. So the big population condition, for that to be met, your population needs to be 10 times bigger than your sample, or you have to be sampling with replacement. Okay, so I don't know if we'll have time to go, or I don't even know if I want to, go over all of the problems that I put in the practice final. So I have posted a solution key for the practice final, but I want to make this time useful for you guys. So if you have a preference for a certain type of problem to go over, we can do that, or if not, we can just kind of click through. So kind of the if we look at kind of the formula page, okay, you can, we have, you know, proportions one sample, hypothesis test of proportions one sample, or hypothesis test proportions two samples. We have confidence intervals with means of one sample, or confidence intervals means of two samples, hypothesis test means of one sample, and hypothesis test means of two samples. So if any kind of one of these categories you want to see more examples of, we can do that, okay? Here it says, can you go over number 11 and those questions for number 11? So yes, we'll go ahead and go to number 11, and we'll work on these problems, okay? So we're going to the ruler and yardstick factory. And so there's a machine that's supposed to produce yardsticks that are exactly 3 feet long, but it's suspected to be defective. So we get a random sample of 40 yardsticks, and we find that the average length is not 3 feet, but 3.02 feet with a standard deviation of 0.03 feet, okay? So is this evidence that the machine is producing yardsticks that are too long? So, so here, because we are dealing with a numeric variable, you know, that has some kind of, that's the length of a yardstick, okay? And you know, the other key clue that it's a numeric variable is we're given a standard deviation. Our hypothesis test is going to be about means. So we've got means. Okay, so it's important that we know whether we're dealing with means or proportions. So we've got means, and then we have one sample, okay? We only have one sample. All right, and here it says it's a hypothesis test. Okay, so the first question, is this a one-sided or two-sided test? The key here is that it says too long, so our answer is that it's going to be a one-sided. And our hypotheses for the next problem, what are the hypotheses? We're going to have a null hypothesis and an alternative hypothesis. The null hypothesis will always have an equal sign. And so here it's asking, it's saying that the machine should produce yardsticks that are exactly 3 feet, and our data is that it produced yardsticks that are on average 3.02 feet. So our null hypothesis is that that the machine produces yardsticks that are 3 feet. Okay, we don't use the numbers from the data here. We use kind of the numbers that we are testing. And then here the alternative is that we want to know if the yardsticks are too long. So we're going to ask if the mu, the mean of the population, is greater than 3.0. Okay, in words it would be something like machine is not defective, working fine. And then the alternative would be that the machine is produces yardsticks too long. Okay. Oh, so for our international friends, the yard is, I don't know, about the length of a meter, and it's equivalent to 3 feet. So, you know, American imperial system of units is all weird. So we have we use feet and yards and inches, and none of it makes sense. But Americans are too stubborn to change their ways, so that's what we have. What is the value of the test statistic? Okay, so for 13, I'm going to come down to here. And so our test statistic is going to be t, and this is going to be equal to x bar minus what's in the mean null hypothesis divided by our standard error, okay? So our standard error is for means of one sample, okay? If we go to the formula, is going to be S divided by the square root of n, okay? So the hypothesis is mu is equal to some number, in our case 3.0. Our standard error is S divided by the square root of n, and T is, the test statistic is X bar minus the mean in the null hypothesis, the mu 0, divided by the standard error. So our standard error, S over the square root of n, is going to be 0.03 divided by our sample size is 40, square root of 40. All right, so I need to pull up a calculator here. Okay, so I got 0.03 divided by the square root of 40. Okay. Okay, so I get 0.00474. 4743. Okay. So this is what I have. All right, so my test statistic, my T, is going to be 3.02. That's my X bar, minus what I have written in the null hypothesis, 3.0, divided by 0.004743. Okay, so I'm going to do 3.02 minus 3 divided by the standard error that I have from the previous problem, and I get a test statistic of 4.216. So that's going to be my answer. Okay, number 14, the p-value for this test. So our degrees of freedom is going to be equal to n minus 1, which is going to be 39 degrees of freedom. And so we go to our t-table to look up 39 degrees of freedom. And okay, so we don't have 39 degrees of freedom. So we can either go to 30 or 40 degrees of freedom. So the general rule of thumb is, you know, round down to be cautious, but I mean, 39 is pretty close to 40. And then, you know, for us, it doesn't really make a difference. Our test statistic is 4.2. So whether I use 40, the largest value is 3.3. And if I use 30, the largest value is 3.385. So our number 4.216 is greater than either of those. So we know that, so what we have is that 4.216 is greater than kind of the number in the last column. What is that? 3.307. What's going on? Why are you barking? Or 3.385, whichever one you use, so it doesn't really matter. 3.385. Okay, and so so that means our tail area, whatever it is, because it's farther away from 0 than this, our tail area is less than 0.001. Okay, So our p-value, we don't need to double it because we have a greater than sign. So our p-value, whatever it is less than 0.001. So that's going to be our answer. Sorry, give me a moment here. Okay. Yeah, I'm not quite sure why he was barking, but he's fine. So okay. So number 15, if alpha is 0.05, what is our conclusion? So our p-value, whatever it is less than 0.05. So we will reject the null hypothesis. That means we conclude the machine is producing yardsticks too long. Okay. Number 16, if the conclusion I made was wrong, what mistake did I make? Okay, so if rejecting the null is a mistake, then this is a type 1 error. Then we committed a type 1 error. Okay. All right. Is that feeling good? Do we have any questions here? Okay, any other requests? Should I just keep going? Should I change it up? Do something different? Do number 19. Okay. All right. So 19 is kind of in the next group of problems. So we'll just go ahead and do this entire group here. Okay. And so this is you can kind of expect. So when I talked about kind of the final exam topics, and I said 20 to 25 calculation-based questions from chapters 7 to 9, you can kind of expect it to be in a similar setup as this, just where I kind of describe a scenario, and in the practice final I put like 6 questions with each scenario, and on the actual final it'll probably be something closer to 4. So but it'll be similar to something like this, where I've described some scenario and then I have maybe around 4 questions related to it, and you can expect maybe 5 or 6 of these types of scenarios. Okay, so we've got researchers believe that 14% of the population is left-handed. A local school decides to see if their students have a different proportion of left-handed people from kind of the nation. And here it says the school has a total of 1,500 students. They randomly select 90 students for the study. They find that 15 of them are left-handed. And is this evidence that the proportion of left-handed students at the school is different from the population proportion of 14%? So our sample proportion, p hat, is going to be 15 divided by 90. Okay, and I think that's what, 1/6. So if I do 15 over 90, okay, we get 1/6 or 0.1667. And we want to do a 90% confidence interval. So what's the critical value z star that we would use? So for 90%, the z star is 1.645. So if I come to the formula sheet, all right, So I kind of list them off here. In the confidence intervals for proportions, we have Z star. 80% is 1.28, 90% 1.645, 95 1.96, and 99 is 2.58. So for 90%, we'll use 1.645. So we'll use Z star is 1.645, okay? And the standard error when we do a confidence interval is p hat times 1 minus p hat divided by n, okay? So for a confidence interval, it's important to remember that you use p hat. Whereas when you do a hypothesis test, the standard error is similar, but you're using p0, the p that shows up in your null hypothesis. So for a confidence interval, we're using p hat, okay? So this is going to be the square root of 0.1667 times 1 minus 0.1667, which is 0.8333. Divided by n, which is the size of my sample, which is 90 here. So when I put this into the calculator, I'm going to have the square root of 0.1667 times 0.8333 divided by 90, and I get 0.0393. That's going to be my standard error. Okay, the center of the interval is just going to be p hat, which is 0.1667. Okay, so in the formula sheet, your interval, the part that comes before the plus or minus, the p hat, this is the center of your interval. Okay, so the center is p hat plus or minus the margin of error. Okay, so make a 90% confidence interval. So that's going to be 0.1667 plus or minus 1.96 times 0.0393. So 1.96 times 0.0393, 0.077. Okay, so we'll add 0.1667 and I get 0.2437 on the upper side. Okay. Let's do 1667 minus 3, and I get 0.0897 on the other hand, 0.0897. Oh, did I used, I made a mistake. Yeah, we should be using 1.645. You are absolutely correct. Not 1.96. Yeah, don't make my mistake. Okay, yeah, Z star, we established 90% Z star is 1.645. So sorry. Thank you for catching that. Okay, so I've got 1.645 times 0.0393. Okay, so that's 1.6. Okay, so on the lower end I have 0.1021. And then on the upper end, 0.2313. Okay, so this is my interval, something around here. Based on your interval, is this evidence that the proportion at the school is different from the nation? So in the nation, we have 14%, so the national proportion is equal to 0.14. And what we look at is 0.14 is inside our interval. So So that means we do not have evidence that the proportion at the school is different from the national proportion. Okay, so there we go. Yeah, sorry about that. Now, 1.645 is the correct number to use there. Okay. Keep going. Something else. So I can do 23, 27. How do we find the center? The center of the interval is always going to be the part before the plus or minus, okay? So center of interval is the part in front of the plus or minus. Okay, so it's always kind of the center plus or minus the margin of error. This is a confidence interval. Okay, and then the margin of error is always equal to a critical value times the standard error. Okay, so all confidence intervals are in this form. Okay, so you've got the center p hat plus or minus critical value z star times the standard error. We didn't do that one, but over here we also have the center x bar plus or minus the critical value times the standard error, and here the center of, when you have means of two samples or a difference, the center is x bar 1 minus x bar 2, that's the center, plus or minus critical value times the standard error. So all confidence intervals are computer is freezing up on me again. Well, here we go. So all confidence intervals are in this form. Okay, maybe I'll do a handful of a few more problems, and then maybe we can just end a little bit early today. All right, so I'll keep going here, and we'll do questions 23 to 27. Is restart that. So let's go ahead and try this one. So it says you buy a bag of Starburst candies and a bag of Jolly Rancher candies. The bag of Starburst candies contains 80 pieces. We'll assume random pieces of candy. All right, 12 of them are cherry flavored. And then we've got some Jolly Ranchers with 70 pieces of candy, and 14 are cherry flavored. And if we assume that these are truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have different proportions of cherry flavored candies, right? So let's figure this out, right? So we want to do a hypothesis test, and we're looking at proportions, right? So we've got proportions, and we've got two samples, and we're doing a hypothesis test. So the appropriate hypotheses. So what we'll do is we'll designate group 1. P1 will be proportion of starburst that are cherry. And then P2 will be proportion of Jolly Ranchers that are cherry. Okay, so our null hypothesis will be that these two proportions, P1 is equal to P2. And the alternative is that they are different. P1 does not equal P2. Okay, the value of P hat. So P hat overall, P hat is the kind of overall proportion. So this will be kind of total cherry divided by total candy. So we're going to do 12 plus 14 divided by the total number of pieces of candy, which is 80 plus 70. So I get 26 over 150. That's 0.1733. That's going to be my overall P hat. Okay. What is the test statistic? Okay. So the test statistic is P hat 1 minus P hat 2 divided by the standard error. The standard error is going to be equal to 0.1733 times 1 minus 0.1733 divided by 1 over n1, which is 80, plus 1 over n2, which is 70. Okay. So that just comes from the formula sheet right here when, why is this not coming to the front here? Okay. So here we have the hypothesis test proportions, two samples, P hat times 1 minus P hat times 1 over n1 plus 1 over n2. Okay. So P hat overall is x1 over n1. You know, so P hat x1 plus x2 over n1 plus n2. We plug that in here. So okay. So let's go ahead and crunch this out. So I'm going to do square root of 0.1733 times minus 0.1733 times 1 over 80 plus 1 over 70, all inside the square root, and I get 0.06195. And so my test statistic T is going to be P hat 1. Oh, I never computed that, so let's do that. P hat 1 is 12 over 80. I believe that's 15%. And P hat 2 is 14 over 70. We get 0.2 here. So I'm going to get 15% minus 20% divided by 0.06195. Okay, so I do, so I'll do parentheses 0.15 minus 0.2 divided by that, and I get negative 0.81. I'm sorry, this is not t, this is a z. Making all sorts of mistakes here. This is z. I apologize. We're dealing with proportions. Anytime you're dealing with proportions, you've got a z. Okay. Okay. So so our z-score is negative 0.81. Okay, so proportions, yeah, we're dealing with z. All right. So our test statistic is going to be z is equal to negative 0.81. Okay, so what is the hypothesis test? So, I'm sorry, what's the p-value of our hypothesis test? Okay, so we go down to negative 0.81. I'm going to find the area to the left, and then we're going to double that because we also want the area to the right because it is a two-sided test. Okay, so the area to the left of negative 0.81 is, so we'll come to, we have to find the z table. Okay, so I look up negative 0.81. The area to the left of negative 0.81 is 0.2090. So this is going to be 0.2090. And this side is also going to be 0.2090. So the total area of the p-value is going to be 2 times that, is 0.4180. All right, so we get a p-value of around 42%, which is really big. So the conclusion is, do not reject the null hypothesis. All right. Okay. How do we feel about this? I hope okay. Are there any other questions? Anything else you guys want me to do? Keep going, keep going. We'll do number 28 as well. Sure. Okay, researchers want to know if drinking caffeinated drinks improves reaction time. So they randomly select the volunteers in a blinded experiment, give some of them caffeinated drinks and others non-caffeinated drinks, and then they record reaction time. So 30 people had a drink containing 300 milligrams of caffeine, and the average reaction time was 580 milliseconds with a standard deviation of 110. And then in group 2, excuse me, we had 25 people had 0 milligrams of caffeine, and their reaction time was 640 with a standard deviation of 130. Okay, and so here we have 2 different sample sizes, so we know that they have to be independent tests. And there's also no indication that, our data is paired. This could have been done in a paired study, and that actually a paired study might have actually been a better design. But in our case, we've got two independent samples, and we're looking at the reaction time which is a numeric variable. Okay, so we're dealing with means, and we have 2 independent samples. Okay, so here, and it asks us if we're going to improve reaction time. So what should the hypotheses be? Okay, so group 1 will be, mu1 will be kind of reaction time with caffeine. And then mu2 will be reaction time without caffeine. Okay, so the hypotheses, the null hypothesis is that with or without caffeine, the reaction time is the same. The alternative is that with caffeine, we have improved reaction time. Improved reaction time means that we take less time to respond. So the alternative is that mu1 is less than mu2, okay? So a lot of these things we have to kind of think about, what does it mean to improve or get better? So improved does not necessarily means bigger or smaller. So in our case, when we are talking about reaction time, we're talking about a decrease in reaction time. That means you're quicker to respond. But in other cases, you know, maybe we would be looking for something different. So here we want to know if the reaction time with caffeine is less than the reaction time without, okay? The observed difference in means, okay? So this is just going to be x bar 1 minus x bar 2. So the difference is the average reaction time was 580 milliseconds minus, without caffeine, it was 640. So the difference is negative 60 milliseconds. Okay, so 580 minus 640 is negative 60. Okay, so the resulting t statistic, so t is going to be x bar 1 minus x bar 2 divided by the standard error. Okay, and again, all of this is on the formula sheet. Hypothesis test, means of 2 samples, x bar 1 minus x bar 2 divided by the standard error. And the standard error is the square root of all of this. Is that S1 squared over N1 plus S2 squared over N2. So we're going to just plug in the numbers that we have. We have 110 squared over 30 plus 130 squared over 25. Okay. So we'll plug this into the calculator. 110 squared over 30 plus 130 squared over 25. Okay, so I get a standard error of 32.85. All right, so my x bar is going to be 580 minus 640 divided by 32.85. Okay, so 580 minus 640 divided by that number, 32.85, I get negative 1.826. Okay, what's the p-value? All right, so my degrees of freedom is equal to n minus 1. Using the smaller of 30 and 25, this will be 24 degrees of freedom. got 24 degrees of freedom. We're going to look up this number, negative 1.826 in the t-table. So I go to 24 degrees of freedom. Negative 1.826 is in between these two numbers of 1.711 and 2.064. Okay, so negative 1.826. So if we ignore the negative, okay, so 1.826 is between what did I say? 1.826 is between 1.711 and 2.064. Okay, so the tail area is between, we go to the column headings here, 2.064, 0.05 and 0.025. Okay, so the p-value, whatever it is, it's between the p-value is less than 0.05 but greater than 0.025. Okay, we have a question. Would it be wrong to assign x1 to 640 and x2 to get 580 and to get a positive difference? No, that's not wrong. You can do it that way. I mean, here I've kind of labeled this one to be group 1 and this one to be group 2, so it kind of makes sense to keep them accordingly. But if you want to call the group with caffeine group 2 and the group without caffeine group 1, that's fine. And you can, and x1 would be 640 and x bar 2 would be 580, and that would be fine. And you'd get a positive difference, and you look up accordingly. But if you do flip them around, then your alternatives will need to be lined up the other way. Okay, so I think on the exam I will label things like group 1 and group 2, so to kind of help you know that when I talk about mu1 being less than mu2, I'm talking about group 1 and group 2 here. So I guess in the case of this problem, you know, because this one does say group 1, the x bar 1 should be the one with caffeine. If they came in unlabeled and we have like the caffeine group and the no caffeine group, then how you label them as group 1 or group 2 is arbitrary. But here I've kind of already labeled them group 1 and group 2, so please respect those, I guess, labels. All right, so this is what we have. Performing a one-sided test with alpha equal to 0.05, what conclusion do we make? So our p-value, I don't know exactly what it is, but I do know it's less than 0.05 and more than 0.025. So our conclusion is reject the null hypothesis, and that means we have evidence that caffeine reduces reaction time. Or improves reaction time. Okay. And if our conclusion to reject the null is a mistake, what kind of error is that? That would be a type 1 error. False positive, a type 1 error. Ooh. Okay. Is this feeling all right? Okay. Well, yeah, there's more of these types of problems in the practice final. If it's okay with you guys, I'm going to just kind of let you guys work through them. And again, I've posted the answers, the practice final answers, for you guys to kind of work through. And then maybe we'll just kind of take a quick look at, I don't know, some of the leftover stuff, which is like conceptual or definition questions from chapters 1 through 6. This is just kind of a taste of what kind of questions you might encounter regarding the questions or definition things for chapters 1 through 6. Oh, and we got a question that says, for lab 5, you gave us all 100%. Yes, so lab 5, I will add a lab 5. Thank you for that reminder. I'll go to the grade book and I'll add lab 5 and give everyone 100% for that. Okay. And then we have another question that says, so there will not be any binomial distribution questions on the final. Yeah, so there's no calculation questions. So you might have a question about like the binomial, like, you know, would you use a binomial distribution for this problem? But I won't have you do any calculations where it says, you know, find the probability of this binomial problem, if that makes sense. Okay, so it could be like, so there could be a conceptual question related to the binomial distribution, but there won't be any kind of questions where I say, you know, calculate the probability of this binomial distribution. All right, so then, all right, so, you know, number 50, it says a bar chart is used for what kind of data? So a bar chart would be used for categorical data, whereas, you know, histograms and box plots are used for numeric data, dot plots and so on and so forth. Number 51, and it says, in a normal model, approximately what proportion of data are within 2 standard deviations of the mean? So this is the empirical rule, and we would expect around in the little cave. Okay. That we're expecting around 95% to be within 2 standard deviations of the mean. So 68% is within 1, 95% is within 2, and almost everything, 99.7, is within 3. Okay. The intercept in linear regression is our predicted value when x has what value, and that's when x is 0. Okay. Whereas the slope is how much we expect y to change when you increment x by 1, things like that. Number 53 says if the probability of A and B happening together is 0, then that means A and B are mutually exclusive. So if, that means they're mutually exclusive, whereas independent means the probability of A happening, whether B happens or does not happen, is just the probability of A. And so on and so forth. Quantitative variable or numeric, quantitative is the same thing as a numeric variable. If there's only one peak in the histogram, how do we describe the shape? That would be unimodal. And then which measure of center is not influenced by outliers? The median is not influenced by outliers, whereas the mean is. Okay. Is this feeling okay? All right. Well, if it's okay with you guys, I'm going to just call it a little bit early, and we'll end class a couple minutes early today. And good luck as you guys study and work through kind of the remaining practice problems. And again, the answers for all of this stuff should be posted online. And we will see you guys on Friday, either at 10 a.m. or 8 p.m. for the final exam. So good luck. And yes, I will have office hours on Thursday. Instead of Friday, I'll have office hours on Thursday at 10. Okay, so I guess I'll note that here. So I guess that's tomorrow. So we'll say office hours on Thursday at 10 a.m. right, you guys, thanks for a great quarter, and thanks for joining me, and good luck, and we'll see you guys on Friday.